So hi, I'm Owen and I'm the first presenter on WDS 07106 plus 1543, a double star. So, some background on double stars. Double stars are stars that appear close together in the sky, and there are two main types. There are true binaries, which are stars that are in fact orbiting each other, and there are optical doubles, which are stars that are not orbiting each other, but instead just look close together in the sky. So, and we studied double stars because if we can find their orbits, then we can find their masses and luminosities, which allows us to find the mass-luminosity relationship for stars in more detail. So, some history on our double star. It was discovered in 1912 by Robert Jean Carré, a French astronomer, who discovered more than 3,350 new double stars during his lifetime. And our star has been measured 21 times since, including our measurement. So now I'll pass it on to Finian.
Yeah, so the telescopes we used to observe our system was the ARCOP telescope in Perth, Australia, and two prompt telescopes, Prompt 2 and Prompt 5, both located in the Andes in Chile. So when we got our images back from the ARCOP telescope, they came back super pixelated, so you can see that from the image. This pixelation made it really difficult to choose an appropriate aperture size to analyze the stars. And when it's difficult to choose an aperture size, then the centroid computation of each star becomes very inaccurate, and your results are generally just unreliable. So when we got our images back from the prompt telescopes, they were so much better. They came back way less pixelated, so we were able to make a really nice aperture size, and then our calculation for the each star was much more precise, and our overall results were more accurate. So in the end, we discarded the ARCOP telescope images and just used the prompt images. So part of our data analysis was making a best fits line of all the historical data points. So a best fits line just shows how close all the points lie to a straight line. And when we did this, we got an R-squared value of 0.995, which greatly supports our hypothesis that we're dealing with an optical double. So here's the graph itself. You can see how all the historical data points lie really close to a straight linear line. So yeah, I'll hand it off to Thomas.
Awesome. So the next step of our analysis was looking at the proper motion data, which basically tells us how the stars are moving across the sky. And we used the visor system to access a lot of catalogs, but most of the data was incomplete, unreliable, or totally different. So we had to do a couple of things to get that a little bit more secure. But as you can see, we have our data points graphed here. And I'll go to the next slide. So the first step of our analysis was analyzing the first data set, which was the UCAC4 catalog. And as you can see from the graph, as represented by the orange and red vectors, the stars are moving in completely different directions at completely different speeds, which suggests different proper motion. And we also apply this to an equation, which if above a certain ratio, it suggests different proper motion. And both of these equations and graphs suggested our conclusion. As well as for the second data set, UCAC5, we had to infer the proper motion of the secondary star because we only had the proper motion of the primary available. In order to do this, we used the historic separation to derive a relative motion and then added those two vectors together. And even with these results, we still found that it represents different proper motion, both from the equation and the graph. And during the review process of our paper, new Gaia data was released, which is a newer catalog with more widely accepted data. And these values as well were very similar to what we inferred from UCAC5 and still suggest different proper motion. So in general, yes, this supports our linear solution and that these stars are not gravitationally bound. And I'll pass it off to Owen
now. Okay, so now I'm going to talk a lot about parallax. So our two stars had parallaxes had distances from Earth of approximately 11,171 light years and 269 light years, respectively, as was measured by Gaia. So that means that the stars are approximately 900 light years from each other, and they can't really be orbiting if that happens. In fact, the primary star would have to be several times larger than the black hole at the center of our galaxy in order for that to be the case, which is very unlikely. So, it's pretty unlikely that these two stars are orbiting based on the parallax data. So, now I'm going to talk about how we found our linear solution. So before you can do that, you need evidence that you have a linear solution, and we had plenty of that. We had proper motion analysis, we had parallax analysis, we had the fact that measurements were deviating from the solved orbit, the fact that a linear trend line fit very well, as you can see in this image above, the fact that a quadratic trend line fit equally well, but that it curved away from the star, and you would expect it to curve around the primary star if the two stars were in fact orbiting each other. So all of that suggested that we had a linear solution. Or that we could find a linear solution. So then we used a best fit linear solution to find. We found a best fit linear solution using a gradient descent algorithm, and we calculated that best fit linear solution to be what's shown right here, and that gave an R-squared value of 0.997. So then we found a best fit linear solution, which had an R-squared value of 0.98, which isn't as good, but it is still very good. It's not as good as the linear solution, but it's still very good fit. But as you can see, it has very extreme parameters, and it's essentially an ellipse modeling a line. So more likely, it's just a line. So in conclusion, WDS 07106 is most likely an optical double, and this is supported by both proper motion and linear solution analysis. So, thank you.